In our next section, we're going to talk about what the periodic table can offer and look into the periodic properties of the elements. So, quantum mechanics not only describes the electronic structure of the atom, it also explains the arrangement of the periodic table. And there are roughly 118 elements in the periodic table. So, to find some order, there is a need to classify the elements. And back in 1869, the periodic law was proposed by Mendeleev and Meyer. And basically, what these guys did is they said the following: if the elements are listed in order of increasing atomic weight, a certain number of properties repeat periodically. Now, there are some exceptions to this. For example, if you look at potassium and argon, if you look at the periodic table, they are not ordered based on the atomic weight. So, because of this, elements are arranged based on atomic number. And a tabular arrangement of the periodic law is called the periodic table. And Mendeleev was given credit for this because when he was listing all the elements back in 1869, not all the elements existed yet, and he left gaps for the elements that weren't discovered yet. So we can classify and kind of describe the various trends that are shown in the periodic table. If we look at the horizontal groups in the periodic table, we refer to these as periods. And the vertical groups in the periodic table we refer to as groups or families. And elements within a particular group have the same properties. So we're going to look into the various ways that we can group elements in the periodic table and look into the trends that we'll observe for these particular groups. In this video, we'll discuss the differences between the main group and the transition metal elements and look at some of their characteristics. If you look at the periodic table in the front cover of your textbook, at the top we can see different groups where we say group A and group B. Group A we refer to as main group elements, and group B we refer to as the transition metals. The main difference between these elements is that group A mainly focuses on the s and the p orbitals and the electrons contained in those orbitals, and the transition metals utilize the d orbitals. So since the bonding is mainly containing s and p in the main group elements and the d orbitals for the transition metals, we need to look at them a little bit differently. So for group A, the number of valence electrons is equal to the group number. So if we look at each of these groups, we have group 1A, which has an ns1 electron configuration, group 2A, which is ns2, and in each of these cases there's 1 and 2 valence electrons respectively. Group 3A has 3 valence electrons, which would be ns2 and p1. Group 4A is ns2 and p2. Group 5A, ns2 and p3. Group 6A, ns2 and p4. Group 7A, ns2 and p5. And group 8A is ns2 and p6. And this is where we get our octet for the sum of the s and the p orbitals that are in a particular atom. And the properties of all of these atoms are based on the number of the valence electrons that it has. So how it will bond, we've looked at charges of cations and anions before. They're all dictated by the electron configuration. Okay? And the reason we place elements in a particular group is because they have the same properties if they have the same number of valence electrons. If we look at group B, which is the transition metals, we see a little bit of different properties, and these elements will behave a little bit differently than the main group. First of all, they're all metals. And when we have transition metals form ions, they become cations when combined with other elements. Another difference with the transition metals and the main group is that they do not normally attain the noble gas configuration. So while main group elements will always form a noble gas configuration, the transition metals, they don't do this as readily. So lastly, when forming cations, they readily lose s electrons and some of the d electrons. So for example, if we have iron, it has an electron configuration of argon 4s2 3d6. If we look at iron 2+, its electron configuration is argon 3d6. Okay? Note that iron 2+ is not 4s2 3d4, it's 3d6. If we look at iron 3+, it's going to have an electron configuration of argon 3d5. Okay, so when forming cations, they readily lose the s electrons and some of the d electrons. In the next series of videos, we're going to analyze periodic trends, and we're going to start with atomic radii. The periodic trend we see for atomic radii is that as you go down a group in the periodic table, the atomic radii is going to increase. As you go across a period from left to right, the atomic radii decreases. So let's look into why each of these trends occur. In terms of the increase that we see, when we go down in the periodic table, we are adding a principal quantum number, or adding energy levels as we go down. So each of these are getting larger, and I think it's fairly intuitive that we would increase the atomic radii as we progress down a group in the periodic table. But one thing that's not as obvious is why would, as we go across a period in the periodic table, would the atomic radii decrease? So what we can say about that is the following. As you progress from left to right in the periodic table, you are adding a proton to the nucleus. But the inner core electrons remain the same. These core electrons are pulled in much more tightly and they become closer to the nucleus. And we refer to this phenomenon as effective nuclear charge, or Z effective. So if we progress from, say, scandium to zinc in the periodic table, each of these guys has the argon noble gas core, which is 1s2, 2s2, 2p6, 3s2, 3p6. So as we progress from scandium to zinc, each of these elements in this series is going to have the argon noble gas core. With scandium, the electron configuration is 3s2, 3d1, and there are 21 protons in the nucleus. As we progress and go over to zinc, the electron configuration is argon 4s2, 3d10. But there are 30 protons in the nucleus. So these 30 protons are acting on the same number of electrons in the inner core electrons of our argon core, versus the 21 protons that are acting on the argon noble gas core. So as we progress from 21 protons to 30 protons, the effective nuclear charge increases. And as a result, when we move from left to right in the periodic table, the general trend that we see in atomic radii is that the atomic radii decreases. So now that we have this foundation, in the next video we can discuss what happens when we go from an atom to an ion and how the ionic radii would be influenced. Now that we've discussed the general trend in atomic radii, we can see what happens when an atom will form either a cation or an anion and analyze the ionic radii. So for cations, we have a particular element and it is going to lose an electron and become a positive charge. So whatever the charge of that cation is going to be equal to the number of electrons it will lose. For example, if we have sodium metal becoming sodium plus, we can look at the relative numbers of protons and electrons to help describe what's going to happen to the ionic radii. So with sodium we have 11 protons and 11 electrons. So if we generically represent the atom, there's going to be 11 protons in the nucleus and there's going to be 11 electrons that surround the nucleus. When sodium becomes a cation, it's going to lose one of its electrons, but it has the same number of protons. So we're going to have 11 protons and 10 electrons. So as a consequence, what happens here when we have one of these electrons removed? So if we remove one electron, what we have left is a scenario where there's 10 electrons. So this is kind of like a tug of war here, and the protons are going to pull the electrons closer to them. So if we have 10 electrons, the pull on the nucleus is going to be much stronger, and as a consequence, we can say that cations are smaller than the atoms from which they are formed. So if we're losing electrons, the protons that remain in the nucleus can pull on those electrons a little bit stronger, and the ionic radii is going to be smaller for a cation as opposed to an atom. We can look at a similar trend for anions. We can represent the anions as gaining electrons. So however many electrons they gain, they're going to have that particular charge. An example we can look at is fluorine. Fluorine can become an F- anion. If we look at fluorine, there are 9 protons and 9 electrons. So if we put these 9 protons in a nucleus and we put our electrons surrounding that nucleus, we're going to have 9 electrons surrounding it. But when we go from fluorine to fluoride, we remain with 9 protons and we have an extra electron. When we add that electron, we now have 10 electrons surrounding the nucleus and there are 9 protons. So this tug of war that we previously looked at for the cation is going to be a little bit different. We're adding an electron, so those 9 protons can't pull as strong as they do when we have 9 electrons versus 10 electrons. So the general trend we can say here is that anions are larger than the atoms from which they are formed. So we can now look at something called an isoelectronic series, which we'll talk about in the next video, which is going to allow us to arrange cations, anions, and atoms in order of increasing ionic radii. One common trend that we typically investigate is something called an isoelectronic species. And an isoelectronic species has the same number of electrons for everything involved in this comparison. So if we look at calcium 2+, potassium plus, argon, chloride minus, and sulfide 2-, we see that each of these have a different number of protons but the same number of electrons. So what we can look at here is how the protons in the nucleus will influence the electrons surrounding the nucleus. And there's going to be a force of attraction between the protons and the electrons. So the more protons in the nucleus, the greater attraction, and the smaller the radii. So when we look at some elements arranged, we first need to figure out how many protons and how many electrons they have. If everything has the same number of electrons, we have a benchmark in which we can arrange these in a particular order. So the smallest in this series is going to have the one with the most protons. So if we look at that, we would see calcium 2+ has 20 protons. The largest is going to be the species with the least number of protons, which is the sulfide. And the order in which these are arranged is in increasing, the increasing radius is in order of decreasing number of protons. So we're going to have calcium 2+ followed by potassium plus, followed by argon, followed by chloride, followed by sulfide. So sulfide is going to be the largest in this particular species. Okay? And we note that all species have the same number of electrons, but we order them from, in terms of smallest over to largest. The smallest has the greatest number of protons, whereas the largest has the least number of protons. So we can do the same exact thing if we compared magnesium 2+, neon, and sodium plus. So if we wanted to arrange these from smallest to largest, we first have to look at the number of protons and the number of electrons we have. Magnesium has 12 protons and 10 electrons. Neon has 10 protons and 10 electrons. Sodium plus has 11 protons and 10 electrons. So we see that this is an isoelectronic series where each of these have 10 electrons. So the smallest is going to be the species with the most number of protons, which is magnesium 2+. Second is sodium plus, and the largest is going to be neon. So this is how we would investigate and analyze isoelectronic species and put them in order of the radii. The next periodic trend we are going to discuss is ionization energy. And ionization energy is the energy required to remove the most loosely held electron from an atom in the gaseous state. So if we look at a particular ionization energy, and the number of ionizations we can have is actually equal to the number of electrons a particular species has. So if we look at magnesium in its gaseous state, it can become magnesium plus 1 electron. It's going to require an amount of energy to do that. And the first ionization energy for magnesium is going to be equal to 738 kilojoules per mole. If we continue to remove an electron from that magnesium, we can get magnesium 2+ plus another electron. And the second ionization energy is going to be equal to 1451 kilojoules per mole. And one thing I want to point out here when discussing ionization energy, the first ionization energy is the energy required to remove one electron from, in this case, magnesium. The second ionization energy is the energy required to remove one electron from magnesium plus. It is not the amount of energy to remove 2 electrons. Okay? That would be the sum of each of these ionization energies. So make sure you keep that in mind when we're looking at these. Another thing to say is that each succeeding ionization is larger than the previous one. So In is going to be greater than In minus 1. And you can see here that when we remove one electron, it takes 738 kilojoules per mole. And to remove that second electron, it jumps up. It almost nearly doubles. So what we can say, and we can generalize this trend, is that the further the electron from the nucleus, the easier it is to remove it. And the general trend in ionization energy that we're going to observe is ionization energy decreases as we move down in the periodic table, and it's going to increase as we move from left to right. So what we can say here, and one of the things that I have to indicate is I need to put a star here next to the increase, because this isn't going to be a linear trend. There is a jagged trend in this ionization energy. So to investigate this trend, let's look at the elements in the second period of the periodic table. So if we look at our ionization energies on the y-axis, and we'll look at the group number on the x-axis, and we can kind of start, we'll start with lithium. So lithium has a fairly low ionization energy. When we go from lithium to beryllium, as the trend suggests, the ionization energy is going to increase. But what we see is when we go to boron, we see a slight drop in ionization energy. Then it will increase again as we go to carbon, then up to neon, or sorry, up to nitrogen. We're going to see another drop when we go down to oxygen. Then it's going to increase when we go to fluorine, and then neon kind of goes off the charts. So the question is, why do we see this type of trend in ionization energy? And it can be explained if we look at the electron configuration. So if we look at lithium, our electron configuration is going to, or the number of valence electrons is going to be 2s1. For beryllium, we have 2s2. Boron is going to be 2s2, 2p1. Carbon, 2s2, 2p2. Nitrogen, 2s2, 2p3. Oxygen, 2s2, 2p4. Fluorine is 2s2, 2p5. And neon, 2s2, 2p6. And when we looked at electron configurations, there were some anomalous electron configurations, and they had to do with kind of how the energy of those electrons are going to result. So in this case, we can kind of see a little bit of stability going from beryllium to boron. There's a discontinuity in the linearity when we go from nitrogen to oxygen. And then everything else kind of goes linear. So the reason these gaps are here is because we find stability from a completely filled orbital, or in the case of nitrogen, a half-filled orbital. So it's a little bit more stable, and when we remove one of the electrons from oxygen, if this electron is removed, we now attain an electron configuration that gives a half-filled orbital. The same thing that happens when we look at boron, if we remove this electron, it now has a filled s orbital. So this is why we see a deviation from a linear trend for ionization energy. We can kind of take this ionization energy topic and we can look at and actually obtain values for each of these. So if we compared sodium and magnesium and looked at the ionization energies, the first ionization energy for sodium is going to be 496 kilojoules per mole, and I'll list all the units in this table in kilojoules per mole. And the second ionization for sodium is 4,592 kilojoules per mole, which is a drastic jump. If we look at magnesium, the first ionization energy is 738 kilojoules per mole. The second ionization energy is 1451 kilojoules per mole. And the third ionization energy is 7,733 kilojoules per mole. So here, for sodium, we see a large jump from the first to the second ionization energy, whereas magnesium, we see a large jump from the second to the third ionization energy. Okay, so this can be, we can look back in the periodic table in the electron configuration. When we take one electron away from sodium, it has the noble gas core of neon. So it's going to be very, very stable. That second electron being taken away is going to require a lot of energy. Whereas magnesium, we take one electron away, it still has one valence electron left. So when we take away that second electron, it's going to reach its noble gas core. So to try to remove that third electron, it's going to take a heck of a lot of energy to do that. So we can kind of look at this then by saying, let's say we have an unknown element that we're going to refer to as X. The question is, what group is element X going to be a part of? So let's look at its ionization energies. We're given values for the first 4 ionization energies. So the first ionization energy is 578 kilojoules per mole. The second ionization energy is 1817 kilojoules per mole. The third ionization energy is 2745 kilojoules per mole. And the fourth ionization energy is 11,586 kilojoules per mole. So the large jump in ionization energy that we see is from 3 to 4. And since we have this large jump, when we go from 3 to 4, we can readily remove 3 electrons, but it's very tough to remove the 4th electron. So this means that this particular unknown element has 3 valence electrons. So it's most likely that this particular element is in group 3. And actually, this is the experimental data for aluminum. So using ionization energy, we can kind of look at the trends and remember, when we're analyzing ionization energy, it's the energy to remove one electron from whatever species we're trying to investigate. And we can then use experimental data to try to predict what group a particular element is in the periodic table. Electron affinity is our next periodic trend, and we can define electron affinity as the amount of energy associated with the gain of an electron by a gaseous atom. So this is kind of the reverse of ionization energy, where ionization energy, it's the amount of energy required to remove the electron. Here it's, I take a particular atom, such as fluorine, and I'm going to give it an electron. Does the fluorine want the electron, or does the fluorine not want the electron? In this case, fluorine has 7 valence electrons, so it would really, really like to have another electron. The electron affinity associated with this, or the energy associated with this, is negative 328 kilojoules per mole. And remember that the more negative the energy, the more stable. So if we have a very negative electron affinity, that means that this is a really good situation. It's going to be very, very stable. So the higher the negative value, the higher the electron affinity. And our general trend for electron affinity, it's going to decrease as we go down a group in the periodic table, and it's going to increase as we move across a period. And again, I put a little star next to the increase because this is not a linear trend. So we can analyze this trend again for the elements in the second period of the periodic table. So if we look at our electron affinity versus group number, we give an electron to lithium, it will take one, right? Beryllium doesn't want an electron as much, so it's going to drop off. Boron will continue to increase and go up with carbon. With nitrogen, it has a half-filled p orbital, so we're going to see a dip in the stability when we give an electron to nitrogen. Then oxygen and fluorine are going to be pretty high because they really want an electron. And remember, each of these species is trying to achieve an octet, so it would like to get 8 electrons. To get 8 electrons, we need to take at least 1. So another thing with the noble gases here is that the noble gases don't want electrons at all. So when we typically represent these, they're going to be off the charts in the opposite direction than they were for ionization energy. So for electron affinity, you need to think of, I have a particular atom, I'm going to give it an electron. Will this want to be stabilized or will it want to be destabilized? And the higher the negative value, the higher the electron affinity. For example, this would be negative 328 kilojoules per mole on the scale, but we represent that as the largest electron affinity. Okay? For neon, the electron affinity is going to be much greater than 0 because when we give an electron to neon, it does not want it, and it's going to become more unstable and not become stabilized. So these are the general trends that you need to look at when we discuss electron affinity. The last topic we want to cover in this section is called magnetic properties. And what we can say about this is the following. Electrons have charge, and they will always spin. This creates a magnetic field. So when we look at magnetic properties of atoms and elements and molecules and ions, we need to come up with some type of standard. And there's a nomenclature that we use. And the terms that we use to characterize this is diamagnetism, which means that all electrons are paired. There's no net spin, or the spins cancel. And there's paramagnetism, which we have a species that contains unpaired electrons. So there's a net spin involved when we're looking at our atom or our molecule. And one of the things that we can use is something called a Gouy balance. And this is going to measure magnetism. So you kind of set up this particular balance, and we could put a weight on one end and use a ruler to measure how much this is going to be displaced. And on the other end of this balance, we connect a sample or a chamber that houses a sample, whether it be our atom or our compound or whatever we're looking at, and then we induce a magnetic field. So the question is, does this magnetic field repel this species right here? If there's a repulsion involved, this balance is going to move. So the more unpaired electrons, the greater the pull, and the more that this particular mass is going to displace. So we can relate magnetic properties to orbital block diagrams. And we can use the periodic table to help us determine what those orbital block diagrams would look like and how many unpaired electrons a particular atom will possess. And again, we'll come back to this concept in Chapter 9 when we look at molecular orbital diagrams. So these are the things that you need to think about when we're discussing magnetic properties.